The topic we are going to study today is formation of complex compounds. A complex compound or coordination compound is formed between transition metals and ligands. Ligands donate lone pair of electrons in the vacant orbitals of transition metals, while transition metals accept the electron pair, making coordinate covalent bonds. Ligand is electron pair donor, so it is the Lewis base, while transition metal accepts electron pair and therefore they are called as Lewis acids. So Lewis base is that which donates the electron pair, and Lewis acids are those which accepts the electron pair. Transition metal complexes may be positive, negative, or neutral. Transition metals form complex ions due to the following reasons. They have small size and high charge density enable them to strongly attract ligands. They have 3D subshell which has low energy and can bond to p orbitals of ligands easily. So they have the high size to charge ratio, and second condition is that they have 3D subshell that has the low energy. Transition metals lose electrons and become cations. They have vacant d orbitals that undergo hybridization to produce same number of new orbitals with equal energy. The process is followed by reaction of ligands with the transition metal ion to form complex. The ligand donate electron pair to the hybridized vacant 3d orbitals of central metal atom. The vacant 3d orbital of first row transition metals are energetically accessible because they have low energy, and ligands can easily donate lone pairs of electrons to them, making dative bond. After this process, ligands come and donate electron pair to those hybridized orbitals, forming complex ion. Complexes of copper 2 with water and chloride ligands. Copper 2 has electronic configuration of 3d9. 6 water ligands approach the copper 2 ions and form 6 coordinate covalent bonds with copper 2 ions. However, before making bonds, the 6 vacant orbitals of copper 2 ion undergo hybridization, generally making bonds. The 6 vacant orbitals of copper 2 ion undergo hybridization, generally generating sp3d2 and sp, and so the sp3d2 hybrid orbitals. These orbitals are then available for 6 water molecules to coordinatively bond and form the given complex as reflected from the electrons in the box diagrams. So 6 vacant orbitals, they undergo hybridization, and hybrid orbitals, they will have the geometry that is sp3d2. So we have vacant 4s, vacant 4p and 4d. So the water molecules will bind with these in these orbitals. So in this way we got the sp3 and d2 structure. Okay. Now we have the example of copper 2 ions intermix 4 vacant orbitals giving 4 sp3 hybrid orbitals. Then 4 chloride ligand coordinatively bond with those 4 hybrid orbitals. So 4s and 4p is available, and these 4 chlorine will hybridize with these orbitals to give the sp3 geometry. With chloride ligands, copper form tetrahedral complex, tetrachlorocuprate 2 ion, because chloride is a big ligand and 6 chloride ligands cannot surround a small copper ion. Complexes of cobalt 2 ion with water and chloride ligands. The condensed electronic configuration of cobalt 2 is 3d7. It forms octahedral complex with 6 water molecules to form dative bonds, and the following diagram shows the formation of octahedral complex, which is hexa aqua cobalt 2. So the geometry will be sp3d2, and Cobalt will also form the complex with 4 chloride ligands to form tetrachlorocobaltate 2 ion. Terminology of complex compounds. Okay, first is what is coordination number? The number of coordinate covalent bonds formed by the metal ions with ligands is the coordination number. The most common coordination numbers are 4 and 6. However, complexes with coordination number 2 also exist. For example, the coordination number of compounds is like for the CuNH3 4, 2 plus is 4, and for the next one is 4, and for FeCN 6 we have the 6 ligands attached, so coordination number is 6, and for the fourth one it's also 6. Coordination sphere. The central atom around with ligands is the coordination sphere. Coordination sphere may be neutral, anionic or cationic. For example, K4FeCN 6 and it is anionic, and CuNH3 4SO4 is cationic, and NiCO4 is a neutral coordination sphere. Charge on the coordination sphere. So it is the sum of total charges on transition metal ion and ligands. Example is Na4FeCN 6. So oxidation state of iron here is +2. The total charge on 6 cyanide ligands is -6. So the charge on the overall sphere is +2 -6, which is -4. CuNH3 4SO4. Oxidation state is +2. Total charge on 4 ammonia is 0, and charge on coordination sphere is +2. Naming complex compounds. Name cation before anion, whether it is simple or complex. While naming coordination sphere, the ligands are named first in the alphabetical order. The suffix "ate" is added to the name of central metal atom. For example, ferrate for iron, cuprate for copper, and argentate for silver. Otherwise, the name of metal remains unchanged. We use the prefixes di, tri, and tetra. So, naming anionic ligands, we use suffix O, which is chloro, hydroxo, and carbonato. Neutral ligands are aquamine and carbonyl. So this is how we name the ligands. We name these coordination compounds. So the ligands are named first in the alphabetical order, and after that we first of all we have to name the cation before the anion. Then we have to write the ligand's name. After that we add the suffix "ate." For example, for the iron we write ferrate, for the copper we write cuprate, and we use the prefixes as well. Naming anionic ligands, we use suffix O like chloro, hydroxo, and the oxidation state of the central ion is present by Roman numerals put in parentheses after the name of metal oxide. Examples of complex compounds are, for example, we have this first is tetraamine. Okay, because here we have the anionic ligand, so we are not writing the name of the ion before the ligand. So first of all we write the name of ligand, and it is in the amine. For example, we have tetraamine, bromo, chloro, platinum 4 chloride. Okay, next one is diamine, copper 2 ion. 2 is basically the oxidation state that should be represented. Potassium hexacyanoferrate, because potassium is a cation, so we need to write its name before the name of the ligand. Hexa aquachromium 3 chloride. Tetracarbonyl nickel. Next one is triamine, trinitrocobalt 3. So this is how we name the ligands, we name the coordination compounds. Working out the charge on complexes and their formula. The total charge on a complex ion depends upon the oxidation state of metal ion and the number of nature of ligands. The oxidation state of metal ion can be calculated from the charge on the complex ion. Remember that oxidation state on the transition metal ion equals to the charge on the complex minus sum of the charge on the ligands. Colored complexes. If light white is passed on the transition metal complex either in the solid form or solution form, some light is absorbed and some is transmitted. If all the light is absorbed, the compound appears black. If some light is absorbed, the compound will appear colored, and if all the light is reflected, the color of the complex compound will appear white. Transition metal ion in solution or solid form are colored because it absorbs a part of visible light, remaining part is transmitted. Light is absorbed by those transition metal complexes which has incomplete 3D subshell. For example, copper 3 complex has incomplete D subshell. On the other hand, zinc it is colorless and it has complete D subshell. Before digging in the topic, we must know about the d orbitals. So here are three conditions, three possibilities that are given. That if the light is absorbed, the color appears will be black. If the light is some light is absorbed, the color will appear there will be some color that is shown, and if all the light is reflected, so that compound will show white color. First of all, we need to see the d orbitals, like we have dxy, dyz, dxz, dx square minus y square and dz square. So in that we have dx square and y square and dz square is are basically along the axis, and dxy, dyz and dxz, these are present between the axis. So consider octahedral complex. While 6 ligands approach the central metal ion along x, y and z, almost all the transition metals of octahedral complex. Interaction between ligands and central metal ion cause splitting of d subshell. Ligands interacting with the two d orbitals are x, y and z experience greater repulsion than that with the d orbitals orienting in between the axes. The higher repulsion results in high energy set of orbitals called Eg, whereas the lesser repulsion gives rise to the lower energy set of orbitals called T2G. First is the Eg and second is the T2G. The overall energy of both Eg and T2G orbitals of the complex is higher than the degenerate 3D orbitals of metal ions without ligand. So here we show the DD splitting. Degenerate 3D orbitals of metal ion without ligands approaching, and there is non-degenerate orbitals. There is a change in the energy. So first the orbitals are degenerate, means they have the same energy, but when the ligand approach, so we can see here that the dx square minus y square and dz square's energy gets high in the Eg. So Eg is basically due to the high repulsion and high energy, and T2G is low repulsion, less repulsion and low energy. Okay, Eg and T2G stands for, basically Eg is for doubly G-rate and triply it's G-rate. Subscript G is basically stand for G-rate, which means that it's a German word, means even, degenerate. Okay. Now we need to see the energy difference between the two sets of d orbitals, and it is equal to the energy of a photon of characteristic light in the visible spectrum. When white light is passed through a complex ion, whether in solution or in solid form, photon of a particular energy and frequency is absorbed, which will excite electron from lower energy set of d orbitals to higher energy set of d orbital. This shift of electron between the two sets of orbitals is called the DD transition. So DD transition is basically the shift of electron from lower energy set of orbitals to higher energy set of orbitals. As a result of this transition, a color from the white light is removed and the solution gives a complementary color to the absorbed light. Different complexes give different colors. So basically DD transition is when white light pass through a complex, whether it's a solution or solid, photon of a particular energy is absorbed, which will excite electron from lower energy set of orbital to higher energy set of orbital. So when the electron jumps from a T2G to EG, so this is basically a shift of electron between two sets of orbitals is the DD electronic transition. And here we have the chart, this color wheel which shows the complementary colors. Like we know that which the color that is absorbed, so the color we see is the complementary color of that. Like if from this chart we can see that if the red orange color is absorbed, we will see the blue green color, and if the violet color is absorbed, we will see the yellow color. So yellow color is a complementary color of violet. So this is how this color wheel works. The nickel complex absorbs red light and appears green, which is complementary to red. Similarly, the copper complex absorbs orange, which appears blue. The DD splitting pattern in octahedral and tetrahedral complexes. So in the octahedral and the tetrahedral complexes, the DD splitting is somewhat different from each other. Let's consider the example of aqueous complex of titanium. This complex is an octahedral shape with 6 water molecules acting as ligands around the titanium ion. In octahedral complexes, the 3 T2G orbitals lie between the 6 ligands, so they experience less repulsion from the ligand lone pair. In contrast, the 2 EG orbitals are aligned directly towards the ligands. Octahedral complexes, based on extent of repulsion between the orbitals and ligands, T2G set of orbitals has lower energy while EG has higher energy. When white light strikes in solid form, solution forms absorb yellow-green light. For excitation of electron gives red-violet color. So this is the color of the complex. Tetrahedral complex, the 3 T2G are oriented towards the ligand, leading to more repulsion. In contrast, the 2 EG orbitals are positioned between the ligands, so they experience less repulsion and have relatively low energy. So in this case, the EG orbitals are positioned between the ligands, so experiences less repulsion and less energy. So the energy of EG is less than the T2G in the tetrahedral complexes. Based on the degree of repulsion between 3D orbitals, electron, ligands, T2G set of orbitals have higher energy, whereas EG has lower energy. For example, consider the tetrachlorocuprate complex. So this is the approach, ligands approaching and non-degenerate ground state orbitals of copper, non-degenerate excited state orbitals of Cu2+. Effects of ligands on color of complexes. When ligands approach transition metal ions, their electric field interact with the d orbitals of metal ions, resulting in the splitting of d orbitals. On the basis of their different abilities to split, strengths are shown. Cn negative has a greater strength than NH3. After that comes water, then hydroxyl, then chlorine, then bromine. So we can see here that cyanide is a strong field ligand. Cn negative is a strong field ligand, and Br negative, Cl negative are the weak field ligands. A strong field ligand splits d orbitals to greater extent, hence causes high splitting energy than a weak field ligand. So when there is a strong field ligand, the splitting is very high, as we can see in this figure. In this strong field ligand, we have the greater gap between the T2G and EG, and for the weak field ligand, there is less gap between the T2G and EG. Consider the addition of ammonia solution to the aqueous solution of copper ions and a subsequent change in color of the given complex. We know that ammonia is a strong field ligand, whereas water is a weak field. So ammonia will place water in complex. In these reactions, 4 molecules replace 4 other molecules, shifting absorption from blue to violet blue. So there is basically 6 water molecules, but 4 ammonia will replace the 4 water molecules, and there is a color change as well. Now we have the geometries of complexes. So in the previous class, we applied valence shell electron pair repulsion theory, Vesper theory on the simple molecules to determine their geometries. So complexes that have the coordination number 4. Complexes at coordination 4, they have the octahedral shapes. 6 donor atoms are present, of ligands are present, both monodentate and polydentate, and octahedral complexes are the most common and stable complexes. The angles between all ligands is 90 degree. Hexaquanickel and tris 1,2 diaminoethane nickel. Complexes with coordination number 4, so they have two different types of shapes like tetrahedral and square planar. So for the tetrahedral, we have the example of CuCl4 2 minus. 4 chloride ligands are at maximum distance, making 109.5 degrees angles. And square planar, they are directed at the 4 corners of square, making 90 degree angle with one another. An example of they are mostly made by the platinum, and platinum complex like diamine dichloroplatinum 2 is the example of square planar complexes. Other examples are NiCN4, AuCl4 and PtNH3,4, and they are mostly formed by the metals which have D8 electronic configurations. And the differences between tetrahedral and square planar is that for the tetrahedral, the complexes are formed between the formed by the metals that have D10 electronic configuration, and for the square planar, the metals have D8 electronic configuration. Complexes with coordination number 2. Linear complexes are stable, so monodentate ligands lying at 180 degree, like diamine silver 1 ion. Other examples are CuCl2 and AuCN2 negative. Okay, that's all for today. Thanks for listening.